to start at the dawn of time, so the invention of type theory around the start of the 20th century. And so to talk about the dawn of type theory, I want to talk about before there was type theory. So let's talk about something called naive set theory. And you know, just as a meta point, if some kind of theory is being described as naive, that probably means there's something wrong with it, or not quite right about it. But one of the key things about set theory is, so on the one hand, and this is not going to be like super technical set theory, but on the one hand, for any set, you have this membership predicate, right, where you can ask, what are the things that are elements of this set, right? Like, is this thing an element of this set X or not? We also have this operation called set comprehension, right, which says that if you have a predicate, then you can comprehend the set of all things that satisfy that predicate. So the reason I'm talking about the membership predicate as well as set comprehension is that these are kind of like inverse operations, because if you comprehend some predicate, then the things that are in that set comprehension are precisely the ones that satisfy the predicate, right? So it's like if and only if. So as a simple example, if you have some predicate that says what an even number is, it doesn't matter how you define it, but it's some number divisible by 2, then from that predicate you can comprehend the set of all even numbers, that's all the n such that n is even, and then we'll have that n is even exactly when n is an element of the set of even numbers. Right? Hopefully that made sense. I've said even a lot of times, but so that seems good. But then so this is usually credited to Russell, but I think actually he was the third person who basically realized there's a problem with this. Russell's paradox is kind of the easiest one to explain, where it says there's something wrong with this, which is that we can consider the predicate of not containing yourself, right? So for set X, we can say that not contain self is true exactly when X is not an element of X. Okay, that makes sense. And then we can comprehend that predicate, so we can say, well, I want the set of all sets that satisfy not contain self. Right? So sets not containing self are just all the X such that X is not an element of X. Now the problem is so does set not containing self contain itself or not? Well, there's two possibilities. So on the one hand, if it does contain itself, then what that means is that it satisfies the predicate, which means that it not contains itself, which means that it doesn't contain itself, and that contradicts the fact that it contains itself. Okay, so I guess it doesn't contain itself, but that seems problematic, because if it doesn't contain itself, then it satisfies the not contain self predicate, so it's an element of itself. So neither of these work, right? So there's some kind of problem here, and this is Russell's paradox. There's also a paradox of Hierarchies and a paradox of Cantor that are basically the same idea, except they're about there's no set of all ordinals, or there's no set of all cardinals. This one is there's no set of all things that don't contain themselves. And so how do we fix this? So this is sometimes called unrestricted comprehension. That does not work. So we can fix it by restricting it. So nowadays set theory has what's called the axiom of restricted comprehension, which says, well, if you fix a set S and then a predicate over S, so not just a predicate over everything, but you have to fix a set and then a predicate over that, then we can form the set comprehension of the elements of S that satisfy the predicate. So you have to fix what you're predicating over. And when you do this, you kind of end up with this stratified theory, or ramified theory, as it was called at the time, which is that, well, first of all, you have some kind of basic objects of the set theory, and then you can have, propositions, and then you can have propositions that are indexed by elements of the basic collection of things. So if you have a function from individuals to propositions, that's like a predicate over individuals. And then when you have a predicate over individuals, you can form the set of of all things satisfying that. And then you can form predicates over elements of that set. You can form predicates over the elements of those sets. So there's kind of a, based on how many times you iterate the set comprehension, and taking predicates over predicates over predicates, you kind of end up with a stratified theory. This was actually the origin of types. Right? So Russell and Whitehead have this, and now everything I'm saying again, I'm a fake logician, so maybe Larry will correct me. But basically, this was the origin of type theory, where the types are basically how higher order the predicates are, right? And this is like Church's notation. Maybe you've seen this this kind of notation before, but this is Church's theory of types, which is kind of a more functional programming looking version of Russell and Whitehead's theory of types. And yeah, I mean, this is basically how set theory works. And I just want to note that, so you have to restrict comprehension, but obviously what you have to not do is also have a set of all sets. Because if you had a set of all sets, now from all the axioms it follows that there is not a set of all sets. But if I were to accidentally axiomatize it in such a way that there were a set of all sets, then we'd be back to the original situation of having unrestricted comprehension. Right? So it's really important here not only that we restrict comprehension to be over subsets of a set, but there also has to not be a universal set. The problem is, it would be really nice if there were a universal set, because there are a lot of times where we want to do something like say, let me talk about the collection of all sets and all functions between the sets. Right? Because say I'm defining the category of all sets, or the category of all monoids, and well, monoids are sets. So there are all these things where I want to talk about all the sets, but that doesn't work because if I talk about all the sets, then I'll be able to derive false. So there's a solution, which is that it is perfectly fine to have a collection of all sets. The problem is that it can't be a set. Okay. It just has to be something bigger. So in set theory, this is phrased in terms of what are called large cardinal axioms. So you can say there's a large set of all sets. These are usually called classes, but there's a large set of all sets. And what properties do large sets have? By the way, a large set is not a set. This is one of those, math things where you add an adjective and it causes it to not be one. Yeah. So there's a large set of all sets, and large sets satisfy all the same properties that sets do. The only difference is, well, A, there's a large set of all small sets, whereas there's not a small set of all small sets. And B, if you do a large set comprehension on a large set, you get a large set. But that's just part of large sets satisfy. You copy paste all the axioms for sets. You replace the word set with large set, and then you add one more axiom that says there is a large set of all small sets. Okay, that's how it works. And then well, that's not enough for me. I can't be stopped. So there's also a huge set of all large sets, and again, you can comprehend over huge sets, and you get huge sets, and et cetera, et cetera. You can do this as many times as you want. Type theorists are monsters. We do this like omega many times because we just don't care. So in type theory, the way that we spell this, instead of saying words like large cardinal axioms, is that we call these type universes. So we have U0 is a type of all small types. And then U1 is the type of all big types, which are axiomatized the same way as small types, except that also U0 is a big type. Right? And then U2, U3, etc. So each of these kind of looks like the other, with the one difference that it also contains the universe that's one less than it. And importantly, of course, we need to make sure that we don't have any of the universes being contained in themselves, because if you do, then you can derive a paradox. Maybe you wouldn't be surprised to find out, even though type theory doesn't have comprehension in exactly the same way. Nevertheless, you can derive a paradox. It's called the Girard's paradox. It's a version of the paradox of Girard. Okay. And the other thing I should mention is that of cumulative. So if you have a small set, it is also a large set. If you have a large set, it's also a huge set. If you have an element of U0, it's also an element of U1, or maybe there's an injection from U0 to U1, it doesn't really matter, but there's U0 is U0 is like a subset of U1, and so forth. Okay, any questions? Okay. So now on to more like type theory. The problem is, it's really unfortunate that U being in U is inconsistent. Because, I mean, actually it's not that inconsistent. I mean, you can definitely prove false with it, but if you're not trying to prove false with it, you actually don't end up doing anything wrong. This is just a kind of empirical fact of like, it only breaks if you're trying really hard to break it. So, why do I want U to be an element of U? Well, for reasons like this. So if you're doing, if you want to talk about the polymorphic identity function, okay, so maybe in system F or something, we write it like this, right? If we, in type theory, the way we write it is we say that, well, for any x, which is an element of U0, you know, I have a function from x to x, right? So I can plug in I could plug in NAT or whatever for x. I have a function from NAT to NAT, right? The type polymorphic identity function. And you can plug in anything for x, except, well, of course, you can't plug in U0. And you also can't plug in U1, but I mean, you can't plug in U0 because U0 is not an element of U0 because that would be bad. So, if I really want the polymorphic identity function, I shouldn't quantify over elements of U0. That's not good enough. So maybe I should quantify over elements of U1. Okay, now well, I can plug in U0, and I can plug in NAT, and I can plug in U0, arrow U0, and I can plug in all sorts of stuff. That's great. Can anyone think of anything that I can't plug in to this function? Yeah, I can't plug in U1. I mean, I also can't plug in U2. But, I mean, right, the U1 is only Apple can plug U2 into your phone. We still can't instantiate with U1. So, okay, well, what do I do? Well, let me pick a really, really big number. So I'm going to say, okay, U 640,000. As Bill Gates once said, 640,000 universes should be enough for anybody. The problem is, okay, well, can you think of something that I can't plug in here? Right, so no matter what number I choose, right, there's always something that I can't plug in here. And you might ask, well, why would you ever want to plug in 640,000 in one or something? Well, the reason is, as soon as I have some type somewhere in my code that has U640,000 in it, well, in what universe does this type land? Well, this type lands in the universe U640,001. So, like, as soon as I utter this type, I have a very good reason to want to talk about U640,001. So that's why you can't just like pick a really big number and just be done with it. As soon as you pick some number, you want the number that's one greater. So what do we do about this? Oh, let me mention, by the way, that so during Paulette's Wonks talk a couple months ago, there was some discussion of predicativity and impredicativity. So basically, being predicative means being stratified by the number of times you iterate predication, right? So that you can only take predicates over things that are kind of pre-existing. And being impredicative is not caring about that, not being stratified in that way. So in system F, I mentioned a bit ago, that's impredicative in the sense that if you quantify over x here, you're allowed to plug in any type whatsoever. You're even allowed to plug in for all x, x arrow x as x. So it's quantifying over everything, including the thing I'm talking about right now, which is why it's impredicative. And generally speaking, I'd say impredicative quantification, sometimes it can be consistent, so in system F it is consistent, but it's impredicative quantification is kind of dubious over sets. It's okay over propositions.
So by subscripting my universes, I made this predicate, right?
Right. Yeah. Right. That's by. Well, I mean, predicative, impredicative. I mean, people get into it. Starts to be like a philosophical debate almost of like what exactly predicativity means. So I think you can actually make a good argument, for example, that the natural numbers are an impredicative construction because part of the definition of natural numbers is that they have this induction principle or recursion principle, and that recursion principle says that for any set where you can exhibit a zero and a successor, that there's a map out from the natural numbers into that. And that for all sets actually includes the natural numbers themselves. So part of the definition of the natural numbers is kind of, depending on how hard line of a predicativist you are, you might actually not like natural numbers for this reason.
Actually, category theory is impredicative from the get-go.
Right, exactly, like all universal properties.
Everything in universal property, that's just one example.
Right. Now, sometimes something has a universal property, but you can define it explicitly. Like, you know, if you want to define disjoint union of things that has a universal property that quantifies over all things including itself, I can also just literally write down a definition of disjoint union of sets. But if you want to assert natural numbers exist, well, you could just say there's an axiom that natural numbers exist. That's what set theory does. But if you want to like axiomatize, like the very axiomatization of natural numbers is kind of like suspiciously.
So it sounds like predicativity is a property of a particular for all in the system.
Yeah.
So
yeah,
you look at this for all and say, oh, by subscripting universes, I made this for all predicative.
Right, and then usually people talk about, right, exactly. And so whether a theory is predicative kind of means like, is there any impredicative quantification in the theory, right? And then you can start getting into like, well, you have a natural number, so is that impredicative? I don't know, you know, there's, these aren't like extremely well-defined notions for that reason, but it basically, type theory is predicative in a way that system F is impredicative. And it has to do with what you can quantify, what you can substitute for quantifiers, right? Can you substitute itself? Okay. So what do we do? Okay, so the problem is that, well, I can't say that U is an element of U because that's inconsistent, but the other solution of indexing by the natural numbers is really annoying, right? And so what do I do about it? Well, one answer would be, well, just duplicate your code. So every time you write down the id 0, and then you want to plug in u0 for x, well, you copy paste, and then you rename it id 1, and then you plug in u0 to id 1, and then you copy paste, and you write id 2. Okay, but I mean, probably that's not how we want to live our lives. It depends. Abstraction, right?
Handwritten slides.
Yeah, handwritten slides. So, what can you do about it? Well, actually, one solution that's not as bad as you might think it is just to say, well, U is in U, I don't care. Because again, in practice, it actually turns out that the only way that you can prove false from U in U is by trying to prove false. Just empirical fact. And so, whenever somebody makes like a tiny little proof assistant, they usually just say U is in U. Don't worry about it. Like, I'll fix it later, and then you never fix it. Another, maybe, more complicated version of the same idea is, well, you just write U everywhere, so you kind of pretend like U is in U, but every time you write U, that means U sub L for some fresh variable L, and then I do some kind of constraint solving problem afterwards, where you say, okay, well, this U has to be bigger than this U because I plug it in for one in this place, and then you solve this system of inequalities, and then you say good or bad. And this is what proof systems like Coq do. Another possibility is you could explicitly declare sets of constraints. So you could just say, this is ui, this is uj, where I is less than j, something like that. Another thing you can do, so what Agnew and Lee do, is that they have explicit level quantification. So there's a type of levels, and you can just write the same way that you write notation for like the quantification over types. You can write a quantifier over levels, and then you just write U sub L, like literally U L, and then you can write things like max of L and L prime, or whatever. You can quantify over a bunch of levels. You can write L plus 1, you can write 10, whatever. So the version of this that kind of makes sense is if you have pre-next level quantification, so that means only as an outermost quantifier we can quantify it over levels. In fact, Agile lets you do more than that, and it's kind of suspicious. Let me, for the rest of this talk, I'm only going to consider pre-next level quantification.
So I guess it's because you're saying that doing a pre-next is like known to be sound.
Right, because doing it pre-next is that you can kind of,
and not doing it pre-next is not known to be sound.
right, or at least what models it has is a lot more complicated. Right, because if you do pre-next quantification, you can think of this like generics or something, where it's like, well, if nothing else, you can literally think of it as copy-pasting all the code everywhere, because you only have an outermost quantifier. So the first thing you always have to do is instantiate it. So I can just copy-paste the definition for every possible instantiation, and that will work. Right? It's like, I don't want to mess with the type system too much, I'm just adding generics, right, in the most kind of restricted way possible. So it's the same exact idea, where it's like very easy to see that pre-next level quantification is like legit, and then it's, in terms of being able to be translated into a no-level quantification system. Non-pre-next quantification, it's like, I don't know how to translate that into normal type, so it's suspicious. Yeah.
So the first three solutions are where I cannot say it is, right? If I want to feed the identity I just defined to the identity I just defined, the same identity.
So this one, it will.
Well, the first one allows you, yeah.
Well, okay, so the first one definitely allows you.
Yeah, anything, yeah.
The second one will see that the two, so it silently quantifies, like every copy of it has a fresh L.
Every copy of it.
Right.
Like copy, like definition copy.
Right, so every time you define something,
Okay. So
every copy of, or every U that occurs in its type gets like, there's a secret quantification over which U it is.
So if I define identity once, I cannot feed it to itself.
No, you can. Because every use of id can be at a different L.
Every use can be at a different. So that sounds equivalent to the fourth solution.
Right, the difference is that this one, you have to plumb you have to find a solution yourself.
So it doesn't add that for you.
Right, so this one is, you can think of this one as this one, but you don't have to write L colon level, and it automatically figures out that this is supposed to be max of L and L prime plus 1, right? This one, you have to write it manually. Yeah.
Can you think of 2 and 4 as in system F, sometimes you don't have the type system infers the type application, and then sometimes you have to specifically supply the type that you want to instantiate over. So, for example, the ID example, if you want to apply ID, you have to say ID square brackets integers applied to some value, whereas if the type checker infers it, then you don't need to provide the type that ID is.
Right, so this one is like you don't have to provide it.
Right.
This one is you do have to provide it. Now, I'll note, like if you do use ACTA a bunch, you can usually make this an implicit argument, and then it will be inferred automatically, but still oftentimes you do have to write, like in the type, like when you define something, you still have to figure out, do the constraint solving yourself, but then when you use it, you can usually have the type checker figure out where to plug in automatically. This one is like even cooler because you don't have to solve the constraints in the first place by yourself.
So 2 questions.
Yeah.
One is, if the level inference solution is equivalent to the quantification solution but with inference, why would you ever want the identity solution?
Right. So maybe you don't want to write a constraint solver. Also, for a long time, the Coq developers actually didn't do this. for a very long time because when they tried to do it, it was very, very slow. And the reason was that because you need every use of a definition to have a fresh copy of all the levels, then it's like, how do you want to type check this? And so their original implementation was you just expand every definition and retype check it completely, and this was really bad. And then they said, I guess that constraint solving doesn't work. And then only like 10 years ago or something, they had it explained to them that there was another way to do it where it's more efficient. But yeah, it's definitely harder and potentially inefficient, and you maybe don't get as much control over exactly what levels everything is. But maybe you shouldn't care.
Well,
Yeah, I guess-
hold on. There's another thing to worry about, which is that when the tool does the inference and then says no to the programmer, what does the programmer do? Right? Like, that can be hard.
Right. Right, although that can be hard in sort of two ways. One is like, the error messages could be bad, which might be annoying, but also it could be that it's not as expressive, which I guess is part of my question, is that like, is the explicit system more expressive than the implicit, fully implicit system?
Right. I guess that ends up depending on exactly how good the implicit system is. So I'm not sure. But one thing I'll mention to Jeremy's point is that a very common thing that like beginning Calc users do is they will be writing some code and then they'll get an error message that says expected type U got type U. That's literally what the error message says. And then if you don't know that you're supposed to type in like show implicits period, reload, then you will never find out that the error message really means like got UL was supposed to be UL prime or something. All right, so that is if you just Google for like people asking why Calc is telling me that U is not the same as U, there's a lot of things.
So, very different question. What do proof assistants or theorem proofers do that aren't type theory based? Since they obviously still, like Russell's paradox is still a problem if you're doing set theory or you're doing simple type theory or something like that.
Right. So I don't want to say something wrong, so I'll say I don't know.
Okay.
Yeah.
Long answers later.
Yeah. But if one thing I'll mention is if you are based on set theory, so while you still have to not fall into Russell's paradox, working in classical logic and having impredicated prop, so the ability to define so it is fine to quantify all overall propositions and to create a proposition because propositions are so small that you kind of run into fewer size issues than you do. Like one kind of maybe issue with, say, like the ADDA type theory out of the box is that not only can you not quantify over sets to create sets, but you can't even quantify over props to create props. You have to create big props. And that's like more annoying. It's okay to believe in impredicated prop, but you should not believe in impredicated set. You should not believe in system F. Okay. So that's my controversial claim of the day. So one final solution that I think a lot of people don't know about, but is maybe a good alternative to just say U and U if you have a prototype proof assistant. So this is kind of lightweight, but actually pretty good, and more on that in a moment, is this idea by Conor McBride called crude but effective stratification. So the way that works is you just write U, and that means U0. But anytime you have a definition, you can apply this bump up shift operator that basically says take all the U's in the definition and bump them by 1. So of course you could bump it by 1 twice. You could bump this by 2 and bump something else by 1, if you want things to all kind of line up. But this is actually pretty good. Like simple, so you don't have to do any inference, but you also don't have to add like a type of levels that has to be prenex or something. It's kind of a good middle ground. Works really well. And if you want a consistent prototype proof system, this is a pretty good way to go.
Question?
Yeah.
I guess with that last one, I'd be a little bit worried that if you have multiple U's appear in the signature,
Yeah.
and they're all being forced to go up at the same rate,
Right.
like does that ever cause problems where like maybe the way you're going to use it is maybe different?
Yes, so that's the downside. Well, first of all, let me note that if you want a definition to talk about U0 and U1 at the same time, that's fine. You can bump one of the U's. So if you just want 0, 1, 1, 2, 2, 3, that's like you can handle that easily. But the worry for this would basically be, yeah, like what if I really want 10 different levels, all of which can be in some, arbitrary sort of.
Or can I bump arbitrary expressions? Like if I applying to a particular argument and maybe it's too low, could I bump the argument up? Or
I think you have to bump definitions because it's again, you kind of think of it as being secretly prenex level conflict.
okay.
Yeah. But if you want to bump the level of an expression, you can bump the function, like if it's a function application, you can bump the function.
Okay.
But there might be a theorem coming up about how well this applies to general situations. Okay. Right, now on to some joint work that I did with Favonia and Reedy Molyneux on an order theoretic analysis of universe polymorphism. So these are called various kinds of universe polymorphism, as you can maybe see from the fact that we're polymorphic over universes. Okay, so first of all, I want to generalize what the universe levels can be. So instead of saying that, well, I have U0, U1, U2, U3, whatever, I can allow any poset. Okay? And now let's think about what are the two principles that universe levels have to satisfy. Well, the first is that U0 is in U1, which is in U2, etc. And I'm going to generalize that to say that UI is in Uj for I and j elements of this poset, as long as I is strictly less than j. So I don't mean less than or equal to, which is the relation of the poset. I mean strictly less than, which you could define, for example, as being, well, less than or equal, but not equal. Or you could say I is less than or equal j, but not j is less than or equal I. Or there are various ways to define the strict order. But so that's the first one. And then the second one is, well, what I was saying before about cumulativity. So if you have an element of U0, then it should be an element of U1. And so for this, we say that elements of Ui are elements of Uj for any I less than or equal to j. Of course, it's fine for I and j to be equal in this example. Yeah.
What's the motivation for this generalization?
Well, you'll see on the next slide. Yeah. So first of all, maybe it's clear, but I could just set the poset to be natural numbers and less than equal to, and that would work. But I can go crazy. So one example is I could say it's the integers and the less than equal to relation. And why would I want to do this? Well, it actually fixes the polymorphic identity function problem without needing universe polymorphism. And the reason is, anytime I have a universe, I can always find a universe that is contained in it. So I can always go down. Not only can I always go up in the natural numbers, but I can also always find something smaller in the integers. Right? So if I have a function that quantifies over U0, and I want to plug in a collection of types for x, there is such a collection of types, it's U -1.
What is the problem that this is solving?
So if I write the polymorphic identity function just without universe polymorphism, so sorry, there's type polymorphic but not universe polymorphic, like this, the U0, then we saw on an earlier slide that that's not going to work because I can't plug in any U for x. So I could either have to duplicate code, I have to have id u0, id u1, id u2, or I have to have some kind of universe polymorphism that lets me plug in different levels for 0.
So this is if I want to apply it to bool to get bool back. Like I think it's.
No, that's fine. I can apply id to bool because bool is in u0.
Sorry. Oh.
I want to apply id at u.
Oh. As something containing bool.
Yeah, right.
Yeah. And use the -1 does contain bool.
Yeah, that's right. Yeah.
What is the consider the fix of this statement value greater or equal to
Sir?
Why is that considered a fix if we still can plug in greater than or equal to in level to the universes?
Right. Well, I mean, being able to do that would let me prove false. So, I guess what I'm saying is that earlier I was talking about how if I don't have quantification over levels, right, then, I mean, whatever level I write, I'm going to have to duplicate the definition to be able to plug in some types, to be able to plug in some universe here, right? So one solution is, well, there's just some kind of generics mechanism for these levels, so I don't have to copy paste the code. But another solution might be that just every universe does contain some smaller universe. You can think of the plugging in -1. If you don't like universe -1, you can think of plugging in -1 as actually kind of shifting everything, right? Whatever the lowest number you ever use is like the new 0. So it's kind of just letting you shift to the left.
So what are the elements of u-1?
So it's all the base types, and then it's also all the universes smaller than -1.
And
Base types have things generated by the base type.
Okay. So like bool is in u-1.
Yes.
In addition to being in u0.
Right, and anything, if A and B are in u-1, then A or B is in u-1.
Yeah.
Also, u-2 is in u-1.
So this just gives us 3 arbitrarily many smaller universes that all have all the base types.
That's right. Yeah.
And they don't have anything else interesting in particular, but
Well, they have u-.
but
It's just like when you write it on the bottom, you're like 640K gotta be good for everyone.
yes,
Right? And that's like, well, let's call that 0 and just allow u minus 640K.
yeah.
Right? So,
Exactly.
So, yeah.
Right. So instead of having to pick the biggest number I need, because that might not never be big enough, why don't I just make it so that I can always go bigger and always go smaller? So then I can never run out of room at 0, right? Because I can always go lower and lower. Okay. Although in the paper there are rules for u sub I, for u sub -10 or whatever. But the rules really are like what I said. So if it's generated by all the normal type formers plus the universes that are smaller than it, strictly smaller than it. Yeah. So it's actually the same as the rules for normal universes. Okay, so if you pick the integers, then you have infinite room to go down as well as infinite room to go up. You could also pick the rational numbers. And not only does this mean you can go infinitely down and infinitely up, but between any two rational numbers, there's an infinite number of rational numbers. So if I want to talk about, there's one type that's in u0 and there's another type that's in u1, right? So normally we'll write something like that, for all x in u0 and for all y in u1, and then you go, oh no, I need like u1 half, because I need something in the middle. Well, have you heard about rational numbers? So now instead of writing constraints like L is strictly less than L prime, or saying L prime is like max L prime or something, now we can just say 0 and 1, and in the same way that 0 is good enough for any, any level shift here, 0 and 1 is good enough for any two numbers where one is bigger than the other number. Okay. Okay. So, I mean, one question you might ask. So you might ask, why is this good? And my answer is basically, well, this means that you can do a lot more before ever having to talk about level polymorphism, right? Like you can actually get pretty far just by saying U0, just living your best life. But an obvious question you might have after why is it good is why is this consistent? Because what I was talking about originally with set theory is this idea that, well, you start with the sets, and then you have the big sets, and then you have the huge sets, and you have the, I guess, how do sizes go? Large with a capital L, huge with a capital H, right? So from that standpoint, I mean, you have the normal sets, and you have the bigger sets, and the bigger sets, and so what does it mean to have like infinite sets going down? That doesn't, like, it's not even obvious it's consistent if you have a non-well-founded poset. And there's actually a pretty simple proof, so you don't have to read all this, but there's a pretty simple proof that it is consistent. And it basically goes as follows. Well, every proof that you write in your proof system is only going to mention finitely many levels. I mean, maybe 1,000, I don't know, but it mentions finitely many levels. And so you can just kind of, maybe the poset is infinite. You can just kind of restrict to the finite part of the poset that's actually being covered. And then when you have a finite number of levels being mentioned, you can kind of linearize them. You can just you can map these onto the natural numbers. You pick you pick a minimum one, and then you keep picking minimum ones until you're done. This only works if you have a finite number of things, because if you have an infinite number of things, you can draw a picture. You can see if you have one thing that's less than an infinite number of things that are incomparable, and then one thing bigger than that, then you can't map it onto the natural numbers. In a monotone. In fact, not just monotone, but strict level preserving way. So what do I mean by that? Well, so if I want the derivations with respect to, so for any poset, right, I should have started here, for any poset, I have a type theory where the universes are indexed by that poset. And what does well-typedness depend on from that poset? Well, it depends on the order, and it also depends on the strict order. So if I have a map from a poset to another poset that is not only monotone, but also preserves the strict order, then any derivation with respect to the first poset of levels will be a valid derivation with respect to the second poset of levels if I just replace every level in the original one with f of that level in the new derivation. Did that make sense? Sam?
Well, I don't understand why the finiteness claim is true.
That there's a finite number of levels? Or that...
Yeah, I mean, it sort of depends on the details of the type theory,
right.
But if we're, like, you might,
There's no level variables.
yeah.
Well, there's no level variable.
Okay,
Yeah.
there's no level variable.
Right.
Okay. Then I agree.
Okay, because the term is finitely big.
Yeah.
So it has finite
I was
numbers
thinking
of
there were
users.
level variables, and then you were going to, it was going to be harder.
Yeah, but this is actually related to Sam's question. That means you actually can't formulate the type theory syntax in the system.
That's correct. The type theory with omega many levels.
You can't formulate it in
Correct. Yeah.
Does that bother you?
No, so it doesn't really bother me. And the reason for that is actually because, so we give you infinitely many levels, but you only ever need finitely many levels at any one time. So I'm actually okay with, so the usual, like in a paper proof or something, we'll either assume that our meta theory has infinitely many levels, or we will say something like, if the meta theory has, n inaccessible cardinals, hierarchy of n inaccessible cardinals, I can model type theory with n minus 1 or n minus 2 universes. And then it also works for other. That's kind of a standard thing. And in fact, so to give the active folks some credit, the reason why they want non-Prenix level quantification is exactly that they do want to prove things about type theory with infinitely many levels in it inside of aggregate. And for that, you need to actually quantify over all the levels and some complicated. But that's a little, like I said, that's a little. At least the consistency is more complicated than in the previous case or the finite case.
So in the theorem statement, we are assuming that all our terms in the type theory are finite?
Yeah.
Okay.
I mean, yeah, that's true. Yeah.
Oh, so that means that we can have infinite terms? That doesn't make sense.
Right. I mean, a term is just like a abstract syntax tree.
Right. Okay.
Yeah. And now you run a term, it might get the term might get bigger and bigger and bigger. But I mean, every term is finite.
Okay.
Yeah. In fact, every term will terminate, so it won't get bigger for forever. But that's a separate question. Yeah.
Is it ever useful to have a poset that's not totally ordered? Because both Z and Q are totally ordered.
Right. Well, yes, because especially when we get to introducing polymorphism, because if you have level variables, right, you might want to say, I have a bunch of level variables and they don't have to be totally ordered.
Yeah. But then earlier you were saying this allows, having Q allows me to not, to get away with not having level polymorphism
For longer.
a little bit longer.
Yeah.
So I'm wondering if you have a poset that's not totally ordered, does that actually help you get away with that for even longer? And it's not clear to me that it does.
Right. So it would. So if you wanted there to be some fixed number of level variables or something. Well, I'm actually going to get to in just a moment where I'm going to extend this further to universe polymorphism. So I will want it to be posets. But there's no reason why it. Yeah. For the purposes of this, I don't have a specific, a concrete example where it's really compelling to have a non-totally ordered thing. In the same way that the natural numbers are as well. Yeah. But it will be useful once we have level variables. Okay, so again, the point is, on the one hand, if you have a strict order preserving function between posets, then that induces a map between derivations in the one theory to the derivations in the other theory. And since terms are finite, they only mention finite and many things, you can map that onto the natural numbers, and so you translate the derivation from L type theory to a derivation in natural number type theory. So if you could prove false in L type theory, then you could prove false in good old-fashioned normal type theory. So that's a proof that it's consistent. I mean, like all consistency proofs, it's relative. So maybe you don't think that type theory is consistent. Maybe you don't think set theory is consistent. Okay. So now let's generalize level polymorphism. So that was generalizing universe monomorphic type theory. Okay, so having just natural number universes, now I have poset universes. What about level variables? So again, if I restricted Prenix level quantification, then you can imagine that you have a context of level variables, and maybe I should be allowed not just to declare a bunch of level variables, but even declare relationships between those level variables, like in Matitas. So you want L as less than or equal to L prime, or something like that. And every time I have level context, so level context I'll think of as a poset. There's a poset of level expressions, let me call H of delta, that are in that context, right? So if the context is just L and L prime incomparable, so that's an example of why I want not a total order, I just have two L and L prime that are incomparable, then maybe all the levels that are valid in that context are like 0, 1, 2, 3, 4, but also L and L prime, but also max L and L prime, and also L plus 1, and et cetera, et cetera. Now, what so first of all, for every poset, I have a poset of level expressions. For every poset of level variables, I have a poset of level expressions. And then what law should it hold? Well, so every level variable should be a level expression. Right, so there's this map from delta to h of delta in posets with strict order preserving maps. Also, if I can map the variables in delta to the variables in delta prime, or two different contexts, so it's like a kind of substitution of variables for variables, then I should definitely get a map from expressions in delta to expressions in delta prime, where you just replace all the old variables with new variables. Right? So that kind of says that h should be a functor. So from a map of delta to delta prime, you get a map from h delta to h delta prime. And then also this should extend to like term substitutions. So if I assign to variables in delta expressions in delta prime, then I should be able to do a substitution and get a map from expressions in delta to expressions in delta prime, where at the leaves of the syntax tree you replace the variables with you splice in expressions. So that written out as a type that looks like this. So in fact, what all this is saying is that h, the kind of assignment of level expressions to level contexts, is a monad on the category of posets and strict order preserving maps. And you don't really have to understand this at a technical level.
Is there a particular edge that you are thinking of, or is this edge something that the designer of a level polymorphic type theory gets to give to you?
That's right. So in the same way that on the previous slide I'm saying for any poset, there should be a notion of type theory relative to that poset, like where you don't have level polymorphism, but the levels range over that poset. There should be a notion of level polymorphic type theory that's so general where I say for any monad on this category, I should get some universe polymorphic type theory. So basically the way that works is there's a new context to the left that's like level variables. And then you can be subscripted by, and in context delta, you can be subscripted by any element of h of delta. And h of delta is a poset, so the rules for those universes are what you think. And if you substitute between level contexts, then you get substitutions between the,
So now if I were to use this, use your work, right? Like I get to decide whether to put negative numbers in h or rationals. And I also get to decide whether to put plus or max.
Right, exactly. So one example of h could be that the level expressions are natural numbers and also variables.
But no max, no plus.
Right.
I can say that.
Yeah, right. But maybe probably a better answer would be like it's natural numbers, level variables, and plus and max or something like that, right? Yeah, that's kind of like the standard. But it could be whatever.
But then if I want that as my edge, what you
Yes.
said, then I have to decide what happens when like plus distributes over max over.
Yeah, you have to decide what the law, because h of delta is a poset, so you have to tell me what the order is.
Okay.
For any input poset.
Okay.
Right.
And then I check these laws.
Right, exactly. And then we prove that, again, for any such h, it's consistent. You can reduce it to the consistency of on the previous slide.
Question.
Yeah.
Is it another way of thinking about H is that you pick your level poset from the previous slides, and then you say, okay, now it's the expressions that you can form from whatever was in that other one, plus level variables, plus max.
Yeah, I mean, you could do, like, that's a reasonable collection of such H's. Yeah.
But you don't have to have max.
Right, yeah, it doesn't have to be max. Well, I mean, such as, yeah. Yeah, well, any, so H is any monad on this category.
Sorry, I was.
Yeah.
I thought it was like, oh, if you do that, then it's a monad.
Right, no. It turns out that this works for any monad.
Okay.
So we have a notion of universe monomorphic type theory for any poset, and then for any monad on posets, we have a notion of universe polymorphic type theory. Okay, so I mean, let me give you another example of what you might want to consider. So this comes from the this idea of crude but effective stratification, so I can bump things up. Right, so you can kind of think of how does that bumping up system work? Well, every term, so maybe let me go back to that slide. Every term is secretly quantifying over some universe levels. Right? When I write U, it really means U sub something. And so every term is in a context with universe levels, prenex quantified. And when I bump things up, that means take whatever universe level that was the input and add 1 to it. Okay? So you can kind of think of this in terms of, well, if the context, the collection of level variables is some poset, then the poset of level expressions in that context is kind of like a product of all of the, so every universe expression is a pair of a variable and a displacement, which is the number of times you should shift it up. So the underlying set is literally the product, and then you have to figure out what the order is supposed to be, and it's slightly complicated. But not talk about that right now. So the idea is that, U sub L upshifted by N is like U sub L plus N. And we represent that as like L comma N. So what are the monad operations? Well, how do the variables get regarded as expressions? Well, the variables are regarded as expressions with a 0 offset. And how do we, if I have L plus N, 1, and I want to add N2 to it, if I have L upshifted by N1 and then upshifted by N2, what does that mean? Well, that means L upshifted by N1 plus N2. And in fact, you can generalize this. So for any, there's this algebraic structure that we invented called the displacement algebra. Like the natural numbers, it's like how much are you able to displace anything, right? And so for any displacement algebra, you get a monad where you have a displacement operator we can displace by any element of the displacement algebra. There's a unit of the displacement algebra. There's a kind of plus of the displacement algebra. This has to be a unit for this has to be associative, and then it has to satisfy some law that kind of makes the double displacement make any sense. So if x is strictly less than y, then z plus x has to be strictly less than z plus y. Maybe you can imagine why that might be important. Yeah.
But the original McBride approach doesn't have any variables.
That's right, but you can think of, but the fact that you can relocate any definition higher means you can think of it as secretly.
So we should think of every use of U as some level variable.
That's right.
But if I write U multiple times, it's not really just every U is a fresh variable.
Right, so it's every U is the same variable. In the original work, it's like every U is the same variable. You can generalize that to say they could be different variables, and then you can generalize that to say the displacement is not.
Okay, so we should think about McBride's original work as there's one variable, which is, your program has one U variable in it, and we just write it on all of the U's.
Well, each definition has one.
Oh, okay.
Has a fresh.
Each definition gets a fresh variable.
Yeah, right. That's universally quantified secretly at the beginning of the definition. But I mean, just to be clear, so even in McBride's original work, he said, well, okay, it's obvious that you can extend this to talk about, more variables. You can extend it to not be on the natural numbers, blah, blah, blah.
Yeah.
So it's not like he didn't realize that that the situation is more general than the one I presented, but we kind of found this like maximally general situation, and then I'll explain in a moment why it made any sense to generalize it in this way. Okay. And so in fact, the main theorem is that for any notion of universe polymorphism, so for any monad on the category of strict orders, then there's actually some displacement algebra. There's some notion of displacement. It might be some crazy notion of displacement, such that the displacement monad, the generalized McBride monad associated to that displacement algebra, contains the original notion of level polymorphism. So basically what that means is we have some definition of what it means to be a universe polymorphic type theory at some pretty big level of generality. The main drawback, the main thing that we don't cover is non-pre-next level quantification. But basically any kind of pre-next level quantification in a generalized sense is included. And then for any such notion, which corresponds to having an H, there is some notion of displacement that will present that original notion. So in other words, if you have a crazy enough notion of what you can upshift by, and how upshifts compose, and what the identity upshift is, then you can present any notion of level polymorphism you have in terms of just upshifting. So this work, many of the results are formalized in ADDA, and then we also have an OCaml implementation of this kind of generalized upshift. So my collaborator Favonia is on this kind of crusade to take proof assistants and break them apart into just a million reusable libraries, so that if you want to invent a new proof assistant, you have to write a little bit of code, and then you just import like 10 different libraries that handle all the complicated stuff. The same way already you will import some parsing library to make your life easier. But now you can also import a universe polymorphism library, where you have to choose what the notion of displacement is, and then in your type checker, you just get to call out to whenever you are trying to type check a universe, you just call out to the library and you say, like, is this universe in that universe, or like, what's it do? And it will handle that for you. So you can define your own displacement algebra, but also we have a bunch of built-in ones, so such that if you want to have displacements for natural number universes, and then later you decide you want to switch to rational universes, you can actually do that by changing like one line of code in your proof system, where you just replace the built-in natural number one with the built-in integer rational. And the OCaml implementation is available. Okay, so I think that's all I wanted to say, so thanks, and I'll take more questions.
Are there any implications on the time it takes for the proof assistant to type check, some proofs using, if you implement it using the generalized upshift versus if you were to sort of just hand roll your level polymorphism?
Right. I mean,
is it just a constant time difference, or could one be like, I don't know what the typical time complexities are for these?
Right. I mean, I guess for all these things, really, if you're not doing some kind of constraint solving, then the level checking part of the type checking process is like zero. if you're trying to actually do constraint solving, then it can potentially be very expensive, as they talked about first time. But I mean, in this kind of regime where we're saying like you have to kind of explain the relative levels yourself, right? The way that, you know, everything except for the cock and level.
So let's say we're in court.
Right, right. Then, I mean, this is, I guess, I don't know concretely, but I think basically all of this is like 0% of the type checking time. And of course, you could have some.
So switching to the generalized option shouldn't change the complexity
Right.
of like a packet or something if it would change.
Right, right. Yeah, I mean, the potential, yeah, like now instead of having, like, quantifying over things yourself, you're using this option calculator. So your code might get easier or harder. Actually, I think some code will get cleaner and some code will get messier. But right, I mean, relative to say, if you had handwritten the displacement operators into your type checker, I think like the difference is 0. In fact, although of course you could define some displacement algebra where your checker for whether something is smaller than something else is very slow. Maybe you did a bad job writing that, and so the log is of course going to be slow. Yeah, there's not really any efficiency concerns.
So, this zero, I think that I'm really expecting that the proof involves more details about the type theory compared to the previous, where you get the proof sketch, where it just feels like all you were using is that the proofs are finite and you can translate it back to some literal thing.
So actually, no.
Okay.
The whole paper, there's actually not that much type theory in the whole paper, and frankly, I was a little bit surprised when the Popple reviewers liked it. Because I was like, I mean, there's of course there's a whole bunch of type theory rules, you know, because we're saying, what are the rules for type theory relative to any post? What are the rules for type theory relative to any, you know, indexed post sets?
Yeah, so you have to give the
right.
The
But then you pretty quickly just say, well, and it's easy to see by almost not talking about the type theory at all that it's consistent for any post set. It's consistent for any H. And those are basically like the arguments that I showed previously. And then now, by the time we're talking about this is like pure, just like reasoning about some algebraic
about the post sets and all that.
Yeah, exactly. There's no type of
okay. So can I use this for polymorphisms that are not universe polymorphism? Like I want effect polymorphism or row polymorphism. It feels like, you know, often I want to like, you know, you start by writing some code and then it's like, oh, that's pure. So I want crude but effective effect polymorphism where I write n map and I bump it to get map m, right? And so on. Yeah.
Right. So I don't know, but I think the considerations there are somewhat different, right? So I wouldn't expect. I mean, I don't think the rules for effect polymorphism look like the rules.
So maybe if you don't care about what the rules look like, maybe it's polymorphic across kinds of polymorphisms.
But the all there is an order. There's no effects have.
Well, sets of effects.
Right, sets of effects are ordered, but there's more to them than the order. There's nothing more to the levels than their relationship.
Yeah, sure, right. You would need more data because then you certainly need to say like which terms are well typed in.
But my generalized level polymorphism theory might have things like there's a special rule, and this special rule only resides in U35 and up, right? Like I'm allowed to ask that, right? In this result. Right?
You say that again?
Like I have a special rule which doesn't reside in any in every universe, except it only resides in universes 35 and up.
No.
No. Oh.
Because then, then this question of like consistency in mapping, then which maps of post sets induce maps of derivations? It starts
So is that like relevant to what you just said?
Yeah, except like the effects have a lot more structure than
Like
what you
reading
just
has
described.
something
Yeah.
and.
Reading has an effect that is different than writing, even though they are both an effect. And like the ordering matters, for example, for effects. The reader monad over the writer over the continuation monad is different than the continuation monad over the reader monad. And whereas we usually think posets do not have that kind of structure. Transitivity is an important property in posets.
Yeah, so I think maybe part of the insight of all this is that very little depends on the universe levels are an important part of type theory, but they barely touch the rest of type theory, right? So much so that you can kind of abstract it away completely and then prove a whole bunch of stuff without ever talking about the rules of type theory again, right? It's so insensitive that I can have the integers and whatever. And I think part of why people haven't done this before is that they think about, and I also think about, the universe levels in terms of the models that we have for type theory with universes. Because you think about U0 means sets and U1 means classes, and you know, in that context, it doesn't make sense to have infinite descending chain of, you know, tiny sets. Right? But the kind of the key observation is that in the syntax it's perfectly fine and consistent to have rational numbers. Now what does that mean semantically? Well, what it means semantically is that the rational numbers are just a funny way of talking about some collections of natural numbers, and we know what the natural numbers mean, right? So it's kind of separating out the meaning from the syntax further, and then you can just start playing around with what we're doing. And that's why the title of the paper is Order Theoretic Analysis of Universe Polymorphism, because actually the paper is not really about universe polymorphism at the end of the day.
It's the universe level 3 half. The meaning of universe level 3 halves does not refer to 3 halves of anything at all.
Right, yeah.
It just refer, you figure out where 3 halves goes, and then it's like, okay, that's 17.
Yeah, I mean, 3 halves, the meaning of universe 3 halves is that it is bigger than universes smaller than 3 halves, and smaller than universes bigger than 3 halves. I mean, in the same way, though, is that when, like, what is the meaning of normal universe polymorphism where you have level variables? Well, the meaning is that you instantiate those levels to be natural numbers, and then that means some obvious thing. Right, and that's why I was saying, like, when you have the non-prenex polymorphism, then the meaning gets a lot murkier, because you actually have to explain what the type of levels is.
Maybe this for after we're done, but asking what that actually means.
In the non-prenex setting. It means that I was able to implement the type checker, so I don't care.
Is there a consistency result for this?
I'm not sure.
Let's think